All right, so how do we describe mathematically a wave? So there are parameters that we will use. Some of them you already know. For example, the frequency, which we will describe with the letter F, which is a quantity that is expressed in hertz or inverse seconds. We can define also, we will see that it's convenient to define a quantity called the angular frequency, omega, which has the units of radians per second, and omega is equal to 2 pi times the frequency. Then another quantity you already know is the period, t in second, and t is 1 over the frequency. So what is maybe new here for you is the concept of wavelengths. Right? So if you have a wave and you describe here the displacement, I choose the axis y for the displacement, and x is the spatial dimension where the wave is propagating. You can see here this wave represented, and you can see a pattern that is repeating, and the length of this pattern is called the wavelength, and we use the letter lambda, and so it's a quantity that represents a distance, so in units of meter. And you note here that, so for example, on this example here, you can choose this repeating pattern from one minimum to another minimum, and this is lambda, or from a maximum to another maximum, this is also lambda, or here from the crossing of 0 and it's going down, here and here, this is also lambda. So the place where you start to measure the wavelengths doesn't matter, because the important point here is that this pattern is periodic in space. And by analogy with the angular frequency and frequency, which represents the frequency in time, we can also define the frequency in space. And we use for this a quantity called the wave number, k, which is expressed in radians per meter, and k is therefore equal to 2 pi divided by lambda. Now, what is the speed at which the wave propagates? Imagine that I create one pulse on a string, okay, and then I continue like this. This pulse, the first oscillation that I created will propagate, and I create the second one. So after some time, I now have these two oscillations here. And if this is periodic, so I have my repeating pattern, and so you see 2 lambda here. Now, how much time did it took for this wave to propagate by a quantity of lambda? You can see that my oscillation has the periodicity of one period and then a second period. So during the second period, this first wavelength pattern will move by a quantity of lambda. So the speed of the wave moved by lambda in the time of t, so the speed is lambda over t. Right? V is lambda over t, or lambda f. Right? And in this chapter, we will only consider kinds of waves where the wave speed is independent of the frequency. So which means that if the frequency is changing, then lambda, if the frequency increases, for example, lambda has to decrease, so that the wave speed is independent from the frequency. Now, it is convenient to describe the wave mathematically so that we can calculate things like the curvature of the string, the power, and so on. And so let's say that we have a wave whose motif looks like this at a time t equals 0. And I want to describe this with a mathematical function. So I have a displacement represented by y here as a function of position x. So I'm looking for a function that could describe this, and the cosine function is actually the one that at 0 would be equal to 1, and at some value 2 pi would also come back to the same value of 1. So the cosine function is a good start here. Now you want that at some distance lambda, we get back to the same maximum, and so for this we can use this x divided by lambda here, so that the function is a, the amplitude, multiplied by cosine 2 pi over lambda x. Okay. Now, at a time t larger than 0, so some time has spent, and this wave is now displaced. Right? So the wave is not just a function of x, but it's also a function of time. And by how much did it move? We already mentioned that the wave speed is v, the letter v. So v multiplied by t will be the distance by which the wave has been displaced. So we can see that this displacement here is equal to vt. Now, if you want to now describe this function, you see that it looks like the same function as before, except that it is displaced, right? And you see that the value at a position x here, for example, I take this x here where the value is the minimum, this value is the same value as the one I had before, but not at the position x, but at the position x minus vt. Right? So what this means is that I can use the same function as before, but I need to replace x by x minus vt. So I get this a cosine 2 pi over lambda x minus vt. And so now I have a function of both position x and time t. Right? Now, we can simplify this a little bit. You see this 2 pi over lambda v here, 2 pi over lambda v. V is lambda over t, so I have 2 pi over lambda, lambda over t. I simplify the lambdas. I have 2 pi over t, which is also equal to the angular frequency omega. And you also recognize here 2 pi over lambda, which we define as the wave number k. So we can finally write this function a little simpler, a cosine kx minus omega t. And this is for a wave that is traveling in the plus x direction. Now, if the wave was traveling in the minus x direction, then I would just have a change of sign here. I would have x plus vt instead of x minus vt. And so for a wave traveling in the minus x direction, the description can be, mathematical description can be a cosine kx plus omega t. Right? And this is called the wave function for an harmonic wave, which in this case is just a simple cosine function. All right, so now that we have a wave function, we can start to calculate certain quantities. So let's say that my wave function is the displacement y is a cosine kx minus omega t. I can already calculate the particle velocity. So if this is a wave on a string, and I want to calculate the speed of a small particle of that string, right? So if the displacement y is given by this function here, I can calculate the velocity by taking the derivative as a function of time, right? So I differentiate this function with respect to time, so I get minus omega here, but cosine gives me minus sine, so I get plus omega a sine kx minus omega t. If you have the velocity, then you can also get the acceleration. Right, so just take the second derivative, and this will give you another minus omega here, so minus omega squared a cosine kx minus omega t. Now, don't confuse the particle velocity Vy with the wave speed, which we labeled as V, right? One represents the speed at which the wave deformation propagates, and Vy represents the speed of the particles which do not propagate along the x direction, but they're actually just displaced in the y direction here. We can also calculate the slope of the string, right? So this would be given by taking the derivative of y with respect to x. So again here, you need to know how to differentiate sine and cosine functions, right? So cosine gives you minus sine, so minus ka sine kx minus omega t. And you can calculate the curvature of the string, which would be the second derivative with respect to x. And so you get this time minus k squared a cosine kx minus omega t. Now you see here these two functions, the curvature of the string and the particle acceleration, both have this a cosine kx minus omega t here. The curvature has minus k squared, and the acceleration has minus omega squared. So we can relate these two functions. Let's say I write the curvature d2y dx squared. It would be k squared divided by omega squared multiplied by the particle acceleration d2y dt squared, right? And now you can transform this quantity here, k over omega. So remember that the wave speed v is lambda over t, right? It moves by lambda in a time in the duration of t. So lambda over t. You can rewrite this as lambda over 2 pi multiplied by 2 pi over t, and you recognize here omega and here 1 over k. So v is lambda over t. It is also omega divided by k. And so here k squared over omega squared is essentially 1 over the wave speed v squared. So 1 over v squared. And so this gives you what is called the wave equation, which relates the second derivative of the displacement with respect to x to the second derivative of displacement with respect to t. Right? And don't confuse what we call the wave equation, which is this, to the wave function, which is the function, mathematical function that describes the displacement. Right? Now this wave equation gives you some useful information. Any function y that will satisfy this wave equation is essentially what we call a wave. Right? So here what we just did is we took this wave function a cosine kx minus omega t, and we derived this so-called wave equation. And so this function satisfies this equation. But in fact, this is more general, and in the LibreText you have a general derivation of this formula, which does not assume any particular function for the wave function, right? So obviously, this could be a sine function as well, and it would work, but it could also be more general and more complicated wave functions. As long as they satisfy the wave equation, then they would represent waves. Now, how do we calculate the wave speed on a string? In fact, the wave speed on a string only depends on two parameters: the tension of the string, T, in Newton, and the mass per unit length of the string, which we will label as mu, and which is a quantity in kilogram per meters. Now, can we guess what is the wave speed, what is the formula for the wave speed as a function of these two parameters? Let's do some experiments. So let's do a pulse on these rubber balls. You see the pulse travels at some speed. Now let's increase the tension. And you see the wave speed is much, much faster when the tension is increased. Again, less tension, the wave speed is reduced. higher tension, higher wave speed. We can also look at the effect of the mass. So here on this torsion wave, I have one that has long bars, so it's like heavier per unit length, and you can see the wave speed. You have the wave propagate like this. Now on this one, the bars are smaller, so the mass per unit length is reduced. And you can see the wave speed is faster. Right? Let me do it again. This is small mass per unit length, high speed, large mass per unit length, and slow wave speed. So we have the wave speed that increase with the tension and that decrease with the mass per unit length. So we can write, I guess, a formula like this. Now you can check the units. The tension in Newton, which is the same as kilogram meter per square seconds. So that forces you to get the square root here. So the wave speed V is the square root of the tension divided by the mass per unit length of the string.